Linear data structures represent the foundation of computer science and programming, organizing information in sequential arrangements where elements follow a specific order. These fundamental structures include arrays, linked lists, stacks, and queues, each serving distinct purposes in data management and algorithm implementation. Understanding linear data structures is crucial for efficient problem-solving and software development. They provide predictable access patterns and memory organization, making them essential tools for beginners and experienced programmers alike. From simple data storage to complex algorithmic operations, linear structures form the building blocks that enable sophisticated computational processes and form the basis for more advanced data organization concepts. Linear data structures organize elements in a sequential, single-level arrangement that's fundamental to efficient computing. These structures maintain ordered relationships, where each element connects to its predecessor and successor. Key characteristics include sequential organization, optimized access patterns, straightforward implementation, and flexible memory allocation options. The four primary examples are arrays with fixed size and contiguous memory offering direct access, linked lists providing dynamic sizing through node-based connections, stacks following last-in first-out principles with push-pop operations, and queues implementing first-in first-out behavior through in-queue-to-queue functions. Understanding the memory allocation differences between contiguous arrays and pointer-connected linked lists is crucial for selecting appropriate data structures. Arrays represent the foundation of linear storage in computer science, functioning as fixed-size collections that store elements of identical data types in contiguous memory locations. This contiguous allocation enables constant-time access through indexing, where elements can be retrieved instantly using their position. The physical proximity of elements enhances CPU cache performance and memory locality. Arrays excel in random access efficiency and simplicity, making them foundational for building complex data structures. However, they face limitations, including fixed sizing, inefficient middle insertions, requiring element shifting, and potential memory waste. Understanding these trade-offs between O(1) access speed versus O(n) modification costs is crucial for optimal implementation. Arrays serve as the backbone for numerous practical computing applications. They efficiently implement stacks using LIFO operations with a top index, and queues through FIFO operations with front and rear pointers. In data retrieval, arrays enable constant-time access in lookup tables and form the storage foundation for hash tables, where hash functions map keys to array indices. Digital image processing relies heavily on arrays, representing images as multi-dimensional pixel matrices. Common operations like filtering apply kernels across image arrays, while geometric transformations use matrix multiplication. Each pixel's intensity value occupies an array element, making brightness and contrast adjustments straightforward mathematical operations on array data. Linked lists represent a fundamental shift from array-based storage, organizing data through interconnected nodes rather than contiguous memory blocks. Each node contains two essential components: a data field storing the actual value, and a pointer field holding the address of the next node. This pointer-based architecture creates dynamic chains that can grow or shrink efficiently during runtime. Unlike arrays requiring costly element shifting, linked lists achieve insertions and deletions in constant time by simply updating pointer connections. While arrays excel at random access with O(1) indexing, linked lists shine in scenarios demanding frequent modifications, offering superior memory efficiency and flexible sizing without pre-allocation constraints. Linked lists come in two fundamental types: singly and doubly linked structures. Singly linked lists feature nodes with data and a single next pointer, enabling unidirectional traversal from head to tail. They're memory efficient but require own time for deletions, since finding the previous node necessitates traversal. Doubly linked lists enhance this design by adding a previous pointer, allowing bidirectional movement through the structure. This additional pointer simplifies deletion operations to O(1) when the node is known and enables reverse traversal. While doubly linked lists consume more memory due to extra pointers, they provide greater operational flexibility for complex data manipulation tasks. Circular linked lists represent a unique variation where the last node points back to the first node instead of null, creating a continuous loop structure. This design enables infinite traversal through the list and eliminates traditional endpoints. Key advantages include efficient head and tail operations with O, 1, complexity, and constant traversal capabilities. These structures excel in practical applications like round-robin CPU scheduling, circular buffers for audio and video streams, multiplayer game turn management, and looping music playlists. Unlike singly or doubly linked lists that terminate with NULL pointers, circular lists provide continuous cyclic flow while maintaining similar memory usage to singly linked lists. Kiaun provides two primary approaches for implementing linear data structures. Arrays utilize STD, array for fixed size containers with compile time constants stored on the stack, while std, vector, offers dynamic sizing with heap-based memory management that can grow at runtime. Linked lists require designing node classes as self-referential structures containing data and pointer fields. Performance characteristics differ significantly. Vectors provide O(1) index access, but O(in) insertion costs due to element shifting, whereas linked lists offer O(1) pointer updates once positioned, but require O(near) traversal for access. Space complexity involves capacity overhead for vectors versus pointer overhead for linked structures. Arrays and linked lists find extensive real-world applications across operating systems and software development. Operating systems utilize queues for process scheduling, with circular lists enabling round-robin algorithms, while linked lists manage memory blocks and file system directories. Software applications leverage stacks for undo-redo functionality and browser navigation, with linked lists powering playlist management. Choosing the optimal structure depends on specific requirements. Arrays excel with frequent random access and cache efficiency, while linked lists shine for dynamic growth and frequent insertions. Key takeaways include understanding each structure's strengths: arrays for static data with O(1) access, linked lists for flexible modifications, and leveraging Jiaoun, standard library tools like std, vector, and std. List for robust implementations.